sample from? We either cored it or we are doing what is known as the reconstituted sample, recompacted sample, right? It's not in situ measurement. Now we are going to talk about in situ measurements, right? In place. It's existing roads, most state projects, productive, repeatable, useful. We all know why in situ testing is needed. One of the most important or most common ones that we talk about in evaluation, pavement evaluation in general, is called falling weight deflectometer. Okay? How many of you have done some kind of stuff on falling weight, like coursework or research or something? Okay. All right. So, what is a falling weight deflectometer? A falling weight deflectometer is basically a hammer that you drop on the soil, on the road, or if you have a very well prepared construction platform, you can test it on there as well. And then you measure what happens to the surface around it. Okay? How do I introduce it in my undergrad class? I say, okay, in America, or well, a lot of you stay in hostels, so it's probably similar, right? In America, when students go to, grad school or something, there is no hostel, right? They have to live in apartments, and the apartments you have to buy very cheap furniture because you're poor. Every student is poor, right? So when you buy very cheap furniture, you have really bad mattresses, gadda, right? When you stand on that gadda, you basically sink, right? Versus you watch these TV commercials, is like, oh, you can do whatever you want and you're not going to wake up your partner, blah blah blah. Remember that, right? So that's what road is basically. A very crappy road, when you load, it's going to sink. A very good road, it's going to distribute the deflections evenly, and it's going to have what is known as a wider deflection basin and stuff, right? So we won't talk about that. So falling weight deflectometer is a pulsed load application. It's an impulse loading which is applied by dropping a load basically that drops here, and then it applies some kind of a pulse, and then you measure, and then obviously that underneath the load the deflection is the maximum. As you go away, the load is going to be, the deflection is going to be small, 0. And this is symmetric. So if you have on the other side, it will look exactly the same, or should look exactly the same if the conditions are the same. So that is called the bowl, deflection bowl, or what is known as a deflection basin, right? And why does that happen, and why is that very relevant? Let's do a distribution comparison here. If you apply a stress load here, and we know the stresses kind of dissipate something like this. Let us just say these are the pavement layers. This is HMA. Let's just say this is base. If this is where the center point of the load is, at this point the deflection is called D0. 0 stands for zero offset, D stands for deflection, and this is the subgrade. What layers affect the deflection of this point? Say it again. All, right? Because this one, this one, this one. If I measure the deflection here, what layer is affecting the deflection here? Only the bottom, because the top is not feeling any stress here because the dissipation has happened. You use that concept when you are trying to calculate your modulus values for layers and stuff like that, which is called back calculation. We'll get into that in a second, right? The whole idea is as you move away from the load application point, the layer that affects the proper deflection or the behavior is going down, 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 down. So that's FWD. What are the FWDs? What is advantage? It's fast, it's inexpensive, results are not affected by boundary conditions, reliable structural number. For pavement design, actually for pavement rehabilitation design, even AASHTO 1993 has a complete method for using FWD to calculate remaining structural life and stuff like that. So this is my example of graduate student mattress versus rich people mattress, right? Weak pavement, you're sinking into it. A strong pavement basically dissipates better, right? Smaller deflection, wider basin. Larger deflection, narrower basin. It's almost like a punching. It's almost like a failure happening, right? Strong pavements versus weak these are just some values. I'm going to skip this. There are many, a lot of research has gone into this for many decades for FWD testing, how to apply the load, because again, remember the load, if you have a steel plate and if you drop a weight on top of it, you are again doing something similar to what CBR does. You're basically punching it. So you have to have some kind of padded contact that dissipates the stresses properly, simulates more like a pressure and stuff. What is the pulse width as well? How much should the pulse be? There is a lot of research that goes into it that we don't have time for it. But this is how deflection is measured. Most FWDs use what is known as geophones. Geophones are what? Who knows? What sensors? They're not acceleration. What do they do? No, geophones don't measure deflection. Geophones give you deflection. Geophones measure velocity. So you have to single integrate them to get deflection. So there are two different types of sensors, right? There is another type of sensor that is based on LVDTs, and they don't call it LVDTs, they call it seismometers. There is a device called QAB that uses seismometer that gives you directly deflection. You know, this Dynatest and everything, they have what is known as geophones. Geophones are velocity sensors. So how do you go from velocity to deflection? You have to single integrate with time and stuff. There are accelerometer based sensors, but not in FWDs. They are based in LWDs and stuff. Okay, so this is how it goes. You basically lower it, you measure it, and then you try to apply a pulse, and this is how the deflection curve typically looks, and then you can then use that. Now there is a concept called back calculation. Now I need to explain what is back calculation, right? I can't teach you to drive in reverse direction unless I first teach you to drive forward, right? The point is, what is back calculation? So if you have a pavement, let's go back to our pavement analysis that we talked about yesterday. You're talking about, I'm going to make it a two-layer system, just easy, E1, E2, mu1, mu2, h1, h2, and then I'm going to apply a load over an area. I'm going to say P comma R. That will give me the stress and stuff like that, right? So P comma R side, and I'm interested in the deflection on the surface at any point. So deflection is a function of P comma PR combination, basically, comma you have layer 1 E1 mu1 h1 and E2 mu2 h2, right? That is deflection. That is your beam theory. Your delta is equal to PL cube over 48 EI or whatever you do, right? That's that. Simple stuff. When you are testing in the roadway, what do you know and what do you not know? Do you know H1? Hopefully, right? Hopefully. Let's just say yes. Do you know H2? Yes, probably, right? Nu1 and Nu2, probably, I mean, it's not very sensitive. So you have like typical ideas, like what's the Poisson's ratio of water? .5. Who said 1? I have a story for you. I was waiting if somebody said 1, I'll tell you the story. And I will not name the professor. I was a student at IIT Kanpur in my 3rd year, 6th semester. And the professor asks, what is a, and I think some people can guess the professor's name. The professor asks, what is the Poisson's ratio of water? And I said 1. And the professor looked at me and he said, I want you to jump out of this window and I want you to have scars on your body for your entire life for saying that. And I was about to cry and stuff. But anyway, it's a joke. I'm not going to make you jump out of the window, but it's 0.5, right? So what is the Poisson's ratio for concrete? No, 0.35 is too high. That's asphalt. 0.15, 0.15, 0.35, 0.3 is close to asphalt. Soil is about aggregate is about 0.3, 0.35. Soil, subgrade soil, you usually take 0.4, something like that. So what I'm saying is Poisson's ratio is not very sensitive. You probably know this. Do you know P? Do you know R? Right? So what do you not know? E, right? So what you're going to do is you're going to back calculate the E. The forward calculation is when you have all the properties and you are trying to find deflection. Oh, by the way, in the field, do you know delta? Yes, because you're running an FWD test. You know the delta. So now you have delta and now you have all the others and you're going to try to back calculate the E. That's called falling weight deflectometer layer modulus back calculation. It's no rocket science. The mathematics there is probably a little complicated, but the concept is very simple. You don't have all the forward calculation properties, so you just are back calculating. How would you back calculate? What you usually would do is I'm going to say, let's assume E1 is say 400,000 psi, E2 is say 40,000 psi, and I am going to plot, this is going to be distance, so radial distance or offset, I'm going to call it offset, and I'm going to call this deflection, okay, and I'm going to say radial offset is 0, deflection is going to be very high, right? As it goes away, 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 deflection is going to go low, 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 right? So this is my predicted basin when I used 400,000 and 40,000, right? But then you go and run an FWD and you are like, my basin actually in the field looks like this. So what did I just do? I under predicted deflection. So I overestimated E. So I should be reducing the E somehow. So maybe I should make it 75, maybe make it 35, something, try to make another line. Then you have another one, you do have another one, ultimately you converge. It's not that straightforward, because if you change the two values together and stuff, you're going to be running and chasing your tail your entire life. You have to have a strategic one, and there are convergence algorithms where they actually do error is equal to delta measured minus delta predicted square summation for all the sensors and stuff, and you just do that, right? So that's back calculation. There are many softwares available. All of them, most of them have some kind of a layered elastic analysis program in the background, and then how they differ is the way they minimize errors and stuff. How's the error minimizing technique and stuff like that. There are several softwares available. A very common question is which is the best software to use. The very good answer is that the software that you know to use the best, right? It's not about which software, it's like how good you are to use whatever you're using, right? You can do the same thing, anything. What are the factors that are affecting load? Yes. Pavement factors, yes. There is layer properties, there is layer thicknesses and all of that. The climatic factors, right? You go in Bhubaneswar and you do in December testing versus you do in July or June mid testing, then your deflections are going to be very different, because asphalt is a stress sensitive temperature dependent material, right? Or if you go to a cold place where freeze thaw happens, you test in December, January, the subgrade is pretty much frozen, your soil, your system looks amazing, but then you go in spring, it is thawed and stuff, it is full of water, it looks like trash. So you have to worry about climatic factors as well. Stress sensitivity, this is something we'll get into in the next couple of days and stuff. The problem with unbound materials is that they are not constant modulus, just like the saran. How many saran wraps you have, it really matters. If you have one layer of saran wrap, it's very weak, aggregate is. If you have multiple layers, it can be a beast, right? So whether you can, when you apply very low value of loading versus a very high value of loading, the behavior is going to change. So pavement factors, what is going to change? Distress. Can you tell me why distress is important? Why is distress important when you are doing FWD testing? You don't understand the question, or you're hungry? Either one is good answer. Exactly. Because the basin happens because of the load transfer and stuff, right? If there is a crack, the load may not transfer. You may actually think that, oh, it's really good pavement, but it's actually because of a crack, it didn't transfer, right? So it's very important. Transverse location, what is that? Where are you with respect to the joints and with respect to the shoulder, with respect to the boundary and stuff, right? Where you are applying. Surface discontinuity, which is similar stuff to joints and stuff. Subsurface variations. I was once working on for Idaho Transportation Department, they gave me some FWD data to help them analyze for some rehabilitation planning, and we had like I think 20 miles worth of data, and we were analyzing at one place. The numbers were just crazy. They were just like crazy. I mean, all of his sudden deflections were like almost like a step function and stuff. And I said, something going on here, go and take a look. And they were able to go and look. They actually saw a pipeline had burst over that location, underground pipeline, and it was completely flooded. And the FWD was just, you had not seen it on the surface, but it was really bad. Underlying voids, very, very relevant for concrete slabs and stuff. When there is erosion happening, washout pumping and stuff, you have really big deflections there and stuff. Random variability also affects. Typical deflection versus time plot. I have told you this a little bit. December, January, February, March, you will have really, really small deflections because this is for a typical North American soil where you have very harsh winter and stuff like that, right? So you have really harsh winter, the water is kind of frozen, subgrade is very strong, but in April it starts thawing. April and May you have really, really bad deflections, and then it starts reducing as well. Yes, in June and July, maybe in the summer the asphalt is probably giving higher deflection, but now the soil has dried up, so it's kind of counterbalancing each other and stuff. So some of that happens, right? So you have to have temperature measurements, you have to have air and pavement, you have to have corrections, you have to compare everything to a standard temperature, otherwise there is no comparison, right? You have to do temperature corrections and stuff like that. 30 to 150 meter intervals, outer lane only. Why outer lane only? What happens on the outer lane? Trucks. Yeah, trucks primarily go on the outer lane if they are following traffic rules, right? But that's kind of, you have to make some assumptions. Both directions you have to have staggered, flexible outer wheel path, JPCP, JRCP, mid slab, joint, corner, because of the deflection patterns are different and stuff. You have to choose where you test. CRCP, it's basically outer wheel path. Interpretation, I'm going to skip this. How do you interpret FWD data? Now this is very important, folks. You all are pursuing some kind of higher studies or something like that, and you are in research right now, and then when you go and you are like, okay, give me a back calculation software, what is it's called, what, IIT back or something, KGP back. So is that still used commonly? Nice. So you are like, okay, give me KGP back, I'm going to be able to use this and stuff like that. The point is, on a daily life for an application or for a practitioner, back calculation is not a very trivial thing, right? A lot of times they look for simpler solutions, right? So there have been a lot of simpler solutions, and you read Professor Thompson's paper last night, and there is one place he clearly mentions that the solutions should be only as complicated as long as they're implementable and stuff like that. Otherwise, it just goes away. So one thing that they do is the deflection basin, they have determined little parameters. This area parameter is not truly an area. I mean, I used to think when I was first exposed to it, I used to think this is the trapezoid area, so it's basically sum of the two parallel sides plus multiplied by height, but it's not. I checked that and stuff. It's a little bit different, but the point is, you see the relationship here, folks. You can set up a very simple Excel spreadsheet to do this. You don't need back calculation, forward calculation, multi-layered elastic programs and stuff like that, right? So what they did is they kind of defined this and said that higher area is basically higher, better structural integrity because it's spreading over a larger width rather than being a sinking thing. That's why you're normalizing with respect to D0 or D1, whatever you want to call it. Then there is another thing called area under pavement profile, or AUPP. What they did is they drew like a rectangle from D0, and then they said this is the deflection. Now I'm going to track AUPP, like whatever is remaining between this deflection and stuff. And then they were able to link that to asphalt modulus, which is log E multiplied by T cube, which is a thickness cube, epsilon AC, which is the lateral strain or horizontal strain in the asphalt layer and stuff. So this is all done mechanistically, and then try to calculate, saying that if this is what your area or your FWD data is giving you, then you should be able to get some idea about what is the strain, what is the modulus and stuff like that, without running full-fledged back calculation. I am not saying this is a replacement for back calculation. I am saying this is a easier way of implementation, right? So one of the best things I like about this approach, and the whole thing that Illinois did and Professor Thompson did, is his work. I mean, when we get introduced to Illipave on Thursday, you will see that Illipave is one of the first finite element based softwares that took care of stress sensitivity of granular layers and subgrades and stuff to calculate pavement response. But what he did is he did all the research in the background, and almost like what you are doing these days, like this machine learning and artificial intelligence, like the big data kind of thing. So he would actually run thousands and thousands of analysis in the background, and he would actually develop typical trends and curves that if your values are like this, this is how it is and stuff. And he would give those values or those curves to the DOT personnel, saying that just use this. Now, if as a researcher later on, when you track this, like, okay, what is the source of this? Then you go back, you're like, man, this is all based on extremely heavy finite element coding and modeling and stuff. But the practitioner is not being bogged down with all of that. They are just having curves or simple equations like this. Like this fatigue equation is probably based on, I don't know, I'm just getting maybe 250 FWD analysis or something like that, or even more than that. It's just in the background. So, but the bottom line is, this is still valid for the areas that they considered. Structural coefficients A1, A2, A3, probably you remember from ASTO 1993, that's the values, so you can actually link them and stuff. ASTO, it actually tells you about how to determine the MR. It actually says, you know, at what distance you are going to get only the subgrade. See this, 24 to 48 inch, that's basically what I wiped over there. So when you have the, man, this marker is falling apart. So it's this. So when you are at least 48 inches apart, away from the load center, it is saying that you are only being affected by the subgrade. So you start from there, and then you keep moving back. Stuff. Back calculation is an ill-posed inverse problem. What does this mean? Do you realize it's an inverse problem, right? What is the ill-posed means? Yeah, it doesn't have a unique solution, because technically you can find E1, E2, E3, E4 combinations, different sets that will lead to the different same basin and stuff. Technically. Practically, will it happen? I haven't seen many times. You still have some certain, you know, values and stuff, but it is actually an ill-posed inverse problem. Again, back calculation programs, ILIBAC, EverCalc, LMod, BoostDef, ModComp, WestDef, ComDef, blah blah blah, FA back, all of them, they are all available. Modulus is something that I have used most, and to some extent LMod. But again, I can guarantee you, as long as you know which one you're using properly, you'll get good answers, you'll get good results. You just have to become an expert on this. This is something I already drew for you, calculated versus actual field. Then you start mixing, then you start moving, ultimately you match. That's basically the purpose of back calculation. Iterative scheme in back calculation programs, I think you know this already. We've taught FWD deflection. So you have load, sensor spacing, seed modulus, layer thickness. You're going to do something like a chevron N layer, or your IIT PAVE, or, you know, min layer, whatever you're going to use. You compute theoretical deflections, and then compare that to the FWD deflections. Is it under tolerance? Yes, then you're good. No, change modulus, go back. That's what happens programmatically and stuff. And you can, with the modern programming abilities and stuff, you can write your own. And on the last day, I'll actually show you some open source resources that you have. Like, actually, I had a much junior, but as a colleague at University of Illinois, who is really big into open source programming. He has actually developed his own Python based layered elastic analysis program that is open source. It's actually available for anybody. So I actually use it in my class. I give it to students. I tell them to play with it and generate multiple things and stuff. So it's, you can just take that, you do it as the forward engine, you have some kind of an error minimization, you have your own back calculation program. Right? These days it's very, very simple. It's not that difficult. Okay, I don't think anything here. Again, Poisson's ratios, we have already talked about it. Poisson's ratios, these are the typical values. You don't really, when you do forward calculation, you will see Poisson's ratio changing, does change the numbers a little, but it's not very sensitive. So Poisson's ratio is something you can pretty much assume and go by. Typical modulus values. I don't know how you all do this, because But when I was a grad student, I was once taught this trick, and I always follow that till date. It's in English units, US customer units, but it's very easy. Just have to remember the number 4. If you take concrete, the modulus is 4 million psi. If it's asphalt, it's 400,000 psi. If it's aggregate, it's 40,000 psi. If it's subgrade, it's 4,000 psi. Representative number, you'll get by with 90% of the cases. Subgrade 4,000 is a little bit on the lower side, but 4 million, 400,000, 40,000 are very, very good guesses for E values if you're doing pavement design and stuff. That's how I use it. Megapascals you can convert, 6.89. Predicted deflections, this is how it works. As I told you, iteration 1, percent difference is 20.5, 1724 was E1, that is the trial, and your delta was, these are the delta values. And then second, look here, what happened, folks. Look, the E1 remains same, E2 remains same, E3 and E4 changes. You know why that happens? Remember what I said is, at D0, what layers affect your properties? All of them. So if you want to match D0 to start with, you're going to be chasing your tail, right? So you have to start from away, only change E4, then only change E3, then go back to E2 and stop. Start from the outside, makes life easier. So that's the reason from iteration 1 to 2, you don't see any E1, E2 change. Here also no E1, E2 change. Here you see a little bit of E2 change now coming. Then you go to E3, E1 change, and then finally you are at an average difference of 0.9%. Any questions? Does that make sense? What was doing here? It's just error minimization. Okay. E bottom is the function of deflection beyond 1 meter, effect of underlying rigid layers. You have to consider that. There is one thing that Dr. Sahu and I we were talking about is the back calc schemes work really well for conventional cases when as you go down the layer quality decreases. If all of a sudden you have a stabilized layer which is actually stronger than the layer above, it kind of goes crazy on you. So you have to have special tools, abilities or skills to address that and stuff. So this is again Illipave based. Log EAC modulus is, look here, this is what I was talking about. Look at the EAC, this is asphalt modulus. What are the inputs? D0, D1, area, temperature, D2, D3 and thickness. What does that mean? A DOT engineer running an FWD test in the field can calculate this on the spot using an Excel spreadsheet or something, or even a calculator if they're good, right? This is what we will play with on Thursday. It's called Illipave. It's a finite element based pavement analysis program that takes care of stress sensitive unbound aggregates and stuff, and you can actually use it for back calculation as well, not directly but iteratively. Like you can predict, check and match and stuff. I'm going to skip this. This is not very relevant. Okay, couple of other things before. I think we're doing good. What slide am I on? Okay. All right. So this is called light FWD or lightweight deflectometer. Okay. So what is a lightweight deflectometer? Like FWD is a vehicle basically. I mean it's a trailer pulled by a pickup or a van or a jeep or whatever you want to call it. It goes and stuff. Now if you have a subgrade construction happening, you're not going to get a vehicle on top of that. It's not possible, and it's not very portable. You probably have one in the state of Odisha or maybe more. I don't know. That's a common challenge, right? What lightweight deflectometer does, it's a portable device. You can carry it on your by yourself. You do the exact same thing. You apply a load, and then here on the plate there are sensors. There you have some accelerometer based sensors as well, which need to be double integrated, acceleration to velocity, velocity to displacement. Some have velocity sensors, some have direct LVDTs or just direct displacement measurements. And then there is a load cell here in some models, some models also don't have any load cells here. Umesh, do you all have an LWD here? What brand is it? Dynatest. So, okay, so if it is a Dynatest, it has a load cell in it. There is another model from Germany called a Zorn, Z-O-R-N or Z-O-R-N. It doesn't have a load cell. There is a different theory to it and stuff. But here, you are only talking about central deflection. One. So, can you calculate different modulus for different layers? With one deflection, can you back calculate multiple layer modulus? No. It's a combination of everything. So what you calculate is something called E foundation or something. It's a composite modulus. There are abilities to extend it like this, offset sensors that you can do, and then some back calculation, but most of them have only one central deflection. You do it and then you measure. Okay, so there is a many German dynamic plate, TRL, Dynatest. I use one that's called Olsen. So in my group we have done a lot of work on LWDs over the past several years. This is usually very good. It's very portable. You have some idea quickly. Deflection, you get some kind of deflection. I have actually developed some compaction protocols that is used in practice for open graded aggregate compaction using LWDs and stuff, saying that, you know, test it, and if it is not less than 0.6 millimeter, go back and compact it again and stuff like that. So those specifications, it's used. I have developed this. Loadman, we're going to skip this. That's my advisor, by the way, from many years ago. This is during my PhD studies. This is a photo, actually. I mean, I took this photo. This is E. What I was trying to show here is there is one deflection. There is a stress distribution factor based on the plate rigidity, and then there is contact pressure, there is radius, and there is Poisson's ratio. But you're basically getting one E. You're not getting multiple E's. It's basically similar to Boussinesq theory and stuff. There is something called SASW, spectral analysis of surface waves, which is again a waveform analysis that is done. Very niche methods. You know, you have to be an expert in surface wave analysis and stuff to calculate modulus values of layers because of this. Basically, they measure the surface waves. Shear wave velocity is related to modulus, shear modulus and stuff, and that's how it goes. Okay, field testing. I think couple of things I wanted to show before we go. I'm going to primarily focus on DCP, dynamic cone penetrometer. I'm sure most of you have heard about it, what they are, how you can do that. One, we'll start with something called static cone penetrometer. I don't know if you have heard about it. It's basically you just hold this and you push it into ground, and then you get a resistance, and then you have some theories or some equations for that. This is the DCP. You have seen this. It's a 60-degree cone. You have a 8 kg hammer falling over a 575 millimeters, and then you drop it. You measure what is known as a penetration rate. The penetration rate is linked to some form of, say, shear strength and stuff. So CBR to DCP correlation is something that's very common. It was originally developed in South Africa, and it's portable, blah blah blah. This is how it looks. There is a measurement stick, and then you measure. This is a very common equation. I would show you some data this afternoon, usage of this, how we calculate CBR using this and stuff. This is called the Klein equation, in inch per blow to CBR and stuff. How many of you have run DCPs? How do you pull it out of the ground? You guys are all that strong? I sometimes on tough soils I have had so much trouble pulling this out. I wish I had something like this. This is a really interesting thing. This is when I was a grad student. This is my PhD project. This is in my group right now. This is like last year's study. So yeah, it keeps happening. Subgrade strength testing just with DCPs and characterization and trying to find the CBR and stuff like that using this. So this is Errol Tutumler. This is my PhD advisor. That's me. And this is an engineer from Illinois. This is what you would end up with by taking the penetration rate and analyzing DCP data. You can find like a CBR profile, and then you can take a, let's just say your area of interest was 6 inches or something. Then you can say, okay, over the first 6 inches, my CBR is on an average this much and stuff like that. That's how soil conditioning in the field happens when you're trying to build test sections, or when you control water and stuff. We can do that. These are a lot of equations for connecting CBR to DCP depending on where you are. The Klein equation is what I use the most. It has worked very well for me and for all projects that I have been involved in. North Carolina DOT developed something, Norway, US Army Corps of Engineers, Israel, Livne, I think they are also, I don't know where they're from, but yeah. And then you have CBR. By the way, today when I go home, after you go, I will send you this document, Garcia-Thompson. It's a PDF document that compares a lot of soil stiffness and strength evaluation methods and stuff. It's a very good read. It's again Professor Thompson and one of his ex-PhD students, Gabriel Garcia. I'll send you this. DCP CBR correlations, again, how they compare. The Klein equation is right here, and then Webster is the black one. NCDOT is over here. It's kind of overestimating the CBR. All the others are kind of close to each other, as you can see. So you just pick one, whatever works, and that's how we have used. This is the one that this is my writing. Yeah, we use it all the time in my group and my PhD as well. Again, correlation chart. You have CBR, you have DCP penetration rate in inches per blow, millimeter per blow, cone index. This is from the static cone penetrometer, just pushing it and stuff. And this is also QU, unconfined compressive strength. Sometimes you have relationships with that as well to calculate CBR and whatnot. Clegg impact soil tester. Again, these are hardly ever you're going to come across. I just have them because these exist. CBR is Clegg impact value square. It's basically it's a QC tool that you drop something, you impact something, and an accelerometer measures small strains. Vane shear, I think some of you may have seen this, right? It's you insert it and you rotate it, and it's basically a shear measurement, just quick measurement of soil quality or soil strength and stuff. This is a very, very important slide. Again, this is going to be in the same document that I have used many times when an undergrad student comes and says, I'm working on this project, can you tell me how I can do this? And I would just go and say, okay, you have uncompressive compressed strength, then just go CBR is divided by 4.5. If you have cone index, go divide by 40 and stuff. Again, empirical, but what are you looking at? What is your objective? Are you doing research in this? Are you wanting to do? Yes, then no, this is not good. But if you're just trying to find a quick ballpark number and stuff, this is very good. Soil stiffness gauge, this is something that doesn't get used as much. I did it quite a bit in my PhD. It's a very small strain vibration that actually induced. So It's a very, and it's like a little suitcase kind of thing that you just carry, put it on the soil, you just ground, you ensure good contact, and then you turn it on, and it applies 20 different frequencies of vibrations and measures the deformation, and then presents something called a stiffness and a modulus, both of it. It's good for near surface measurements. So for example, if you have a thin layer, like you have only like a 3-inch thick layer or something, then if you do an LWD or something, the influence bowl is going to go beyond that 3 inches and stuff. This gives you a good number and stuff. There's 10 kg weight, and it applies different frequencies, and then it just measures you modulus and stiffness. And see, a modulus of the top 0.1 to 0.2 meter, like 4 inches to 8 inches of a wide range of soils. Cannot measure on wet soil and hard paved surface. So not at all on a stability base or something. You're going to get garbage. It's just going to get vibrated. This is from my PhD work. Very small vibrations. This is the relationship. It gives you Young's modulus and shear modulus and stuff. This is just some display we had in one of the projects. This is actually an interesting thing. Vane shear test, easy to use, yes. Clegg impact, yes. Light drop weight tester, yes. GeoGauge, yes. Experience in research, vane shear, yes, you have quite a bit. Clegg impact, not really. Light drop testers and GeoGauge, no. What do you measure? Vane shear measures shear strength. Clegg impact measures kind of CIV, and then you can correlate to CBR and MR. Lightweight drop tester, deflection modulus. Now this thing, it's old, but now it has changed quite a bit. There has been a lot of research. Assumes that max deflection is elastic. This is a very standard problem or standard assumption when you are applying even in FWD. When you are applying the pulse and you're measuring, is it all elastic or you already accumulated some plastic that is being accounted for that, right? So that's something. Static cone, dual mass, you can take a look at that. Testing versus traffic loading, load duration, load magnitude. Impact devices have a very, very high load magnitude, but small load duration. But GeoGauge or something, you have very, very small load magnitude. You're taking really, really small strain measurements, right? But you're measuring over a larger duration and whatnot. Again, this is during my PhD, a couple of graduate students helping me during my work. They're both professors. This is actually one of the, I'm going to show this, and I think we can probably end it here. This is a plot from my dissertation, and as you can see here, so there are 3 sections, okay? So all the closed circles and closed triangles or filled triangles are LWD, and all the open ones are GeoGauge, the vibration. So the same things being tested, 2 devices, okay? So section 1 is the black, and if you see here, the GeoGauge small strain usually gives larger modulus, that's why it's higher. Red, again higher but similar range, but 3, something happened and you actually saw LWD actually all over the place, but GeoGauge was very, very high, okay? So as you can see, like this similar range and this similar range. So we were like, what's going on? Why is the GeoGauge in this case is consistently high, whereas the LWD was, bouncing around and stuff. So then we went back to take a look at this, and this is actually another thing. What you will see is the average CBR was 3, average CBR was 2.7, very close to 3, but this is actually about 3.9. So CBR was actually higher, so it's actually a stronger layer, okay, but LWD was not able to catch it. It was bouncing around because the layer thickness was also small, so it was also being affected by the subgrade. Whereas the GeoGauge isolated it and said that, okay, it's good. So this was one example where it actually worked better in identifying the cause of what was going on, significantly stronger than the other two sections. And this is what it was. And look here, section 3, even relative compaction was the highest, 96.2, but LWD modulus was not showing that, but GeoGauge modulus actually was actually tracking it, because it was able to isolate, because it's within the layer and stuff. So what are the problems? Subgrade evaluation, you have to have so much value, you have so many test results, right? Anywhere between 10 to 100. What is the representative value? Do you design for the worst condition? Do you design for the average condition? Do you design for a percentile or so? That depends on who you are working with, your specification and stuff like that, right? We are going to have engineering properties as a function of time, strength considerations, change in moisture, as built subgrade, soil type, local effects, which is drainage grade and stuff, swelling soils, frost action and stuff like that. And you have to sometimes DOTs would establish something like a typical value, which is CBR, unconfined compressive strength. I haven't gone into ERI yet intentionally. I'll show you that when we go into resilient modulus. It's related to modulus, breakpoint modulus. Again, some typical values. I don't think we need to go over any of this. What changes? This is a modulus. When 1% moisture increases and stuff, loam and silt had the highest percent change in modulus versus clay. Clay is very sensitive, but when you change 1% or something, it doesn't collapse like that, but silt would actually collapse a lot of times. So that's it. That's pretty much it. Right on time. Good planning, right? But yeah, so that's pretty much it for subgrade evaluation. What we are going to do is we're going to break for lunch. When we come back, I will show you some typical triaxial shear strength data, and I'm going to share that with you. And then I will show you a spreadsheet how that was used to plot more circles and tangents, and you can get working. And I will also show you a MATLAB code that we developed in my group to automatically read the files and plot them and show. So it's going to be a good exercise. Oh, and we'll start with looking at your spreadsheet from yesterday if you finish that one. Okay, that's it. Thanks.